arc length. By arc length, I mean how long the actual curve is. As if I could take the string that maps out this space curve. How long is the string? So, I mean, in this particular curve, we're going round and round and round and round. How far is it all the way around that path? That's what I mean by arc length. And the way we're going to get to it is I lost my pen. If we think about then a space curve like that, what I'm going to do is take snapshots of it, where it is at time 1, where's the point at time 2, where's the point at time 3, etc. So we're going to discretize this curve by taking discrete times and then measuring the straight line distance in between these points. So these are supposed to be straight lines. And then add up the distance, add up all those straight line distances. Now this straight line distance between these 2 points, I can get that with Pythagorean theorem. If I say that this is some time, let's say ti, and this is the next time, ti plus 1, then when I take the snapshot here and when I take the snapshot here, there's a delta t, a change in time. Now obviously if I take the snapshots faster, there's shorter time in between, and the discretization, those flat lines, they better hug the curve, so I get a better answer. The shorter my delta t is. Now, this is my change in the x. Now I'm drawing this in 2 dimensions. Our formula, I'll derive it in 2 dimensions, but you can see how our formula extrapolates up into 3 dimensions because we know the distance between 2 points formula. Really what I'm doing here is I'm using Pythagorean theorem, little right angle there, but I'm getting the distance between these 2 points. This is the change in the y value. If it was in 3D, there would be a change in the z value. So this little change, I'm going to call this little change in L, the distance in the length. So how much the arc length is increased from this point to this point. Little change in the L is equal to, well, Pythagorean theorem, square root, the change in the x squared plus the change in the y squared. There's the little change in the L. That's this distance. And from this is given by at time ti, and yeah, from ti to ti to the next time, t sub I plus 1. Now if I want this whole curve starting off when, let's say I want to start when t is equal to a, that's the starting time, and I want to end over here when t is equal to b, that's the ending time. I want this whole time. I'm going to chop it all up into these discrete times and then add up all those delta L's. So I'm going to sum up all those delta L's. So I'm summing up all of these square root of x squared plus delta y squared. I'm summing all of those up. And if I make the limit as the number of times, let's call n the number of times, the number of snapshots I take. So I'm going to take the limit as n, the number of times as we start from a and go all the way to b. I'm going to take that limit as n goes to infinity. Now limit as n goes to infinity of a sum, so starting off at t equals 1, let's say, and going to t equals n, because there's n of those snapshots, this starts to look like our familiar limit definition of an integral. Yeah, that's exactly where I'm going. But I need to know with respect to what am I integrating? Because there's a, usually when we take our limit sum and that morphs into an integral, there's some distance that goes to 0, like a delta x goes to a dx when we're doing our area under a curve with rectangles. And here I've got sort of 2 things, a delta x and a delta y. As the time between snapshots goes to 0, as n goes to infinity, the delta t does go to 0, but the delta x shrinks to 0 and the delta y shrinks to 0. They shrink at different rates depending on where what the slope is. So what I would like to do then is, as n goes to infinity, our delta t goes to 0. So I want this to be integrated with respect to dt. So I'm going to take this expression. Before I take the limit, I'm going to multiply top and bottom. I'm going to multiply by dt over dt. I'm just multiplying by 1. But this bottom delta t, I'm bringing inside the square root sign. If that bottom delta t goes inside the square root sign, it becomes squared. So I'm bringing that one inside, and it's going to be delta t squared and delta t squared here. Now I've got delta x over delta t all squared. So let's clean this up. Let's go to the actual typing thing and clean this up. We do that? No, let's put an arrow over here. Okay, so right now I've got the limit as n approaches infinity, which means delta t goes to 0, of the sum from I equals 1 to n of the square root of, now that's delta x over delta t squared plus delta y over delta t squared square root, and there's still a delta t out here, a little change in time. Now, as t goes to infinity, as n goes to infinity and the delta t goes to 0, this here looks like y, that looks like x, that looks like the x prime, right? As delta t goes to 0, that becomes the limit of the secant slope. That's x prime. That's y prime. This delta x goes to a dt as we morph our limit sum into an integral. So this whole thing becomes the integral, that's what all this becomes, from a to b, square root of, now I need some space here, x prime squared plus y prime squared dt. Now, as I've got the dimension that's going to 0, that's the change in time, the delta t, that morphs into the dt. There's my integral. But let's take a look at this. What's this square root of x prime squared plus y prime squared? Oh, and if there was a 3D, there would be a plus z prime squared. That's, okay, now let's go back to here. Let's go back to here. Yeah, no, I'm still writing here. Let's make some space because there's a lot of stuff here. And I guess I can, I don't know that line. Okay, so this is our integral, which is supposed to be the arc length. But remember, if I had a function, r of t, the vector function whose arc length we're given, and I differentiate that function to give me the, well, we called it the tangent vector, right? The derivative of the tangent. That would be the x prime, the y prime, and if there was a z here, it would be the z prime, but we don't have that right now. But that's the tangent vector. If I wanted the magnitude of that tangent vector, the magnitude of any vector would be the square root of first component squared plus second component squared plus third component squared if I'm in 3D. Now I've got that. It says derive the arc length. We did that. The arc length from t equal a to t equal b, starting time and ending time, is the magnitude of the tangent vector. That's the formula that we made. So, derive the arc length formula, done. But I mean, this is a nice, neat way of writing it, but let's recognize that this magnitude of, that means the square root, big square root sign of the first derivative, the derivative of the first component squared plus this, this is what I'm trying to do. And let's put a z in there. I know we didn't formally derive it, but we saw how the pattern. So x prime, y prime, and z prime. So the formula itself has a big square root sign in it, and we got to integrate. So actually solving these integrals, getting a value, getting a number, the integration is sometimes hard. Most of the time, in fact, generally it's impossible. So we have to use some kind of a numeric way to do it. When they ask you to do one of these on a quiz or a homework or something, it'll probably be doable, and that means the thing under the square root sign will either be a line when I simplify it or a perfect square. Those are the things to be looking for. Anyway, let's look at an example. Here's a spiral. What's the arc length from t equals pi to t equals 4 pi? So let's set this up. The first thing I'm going to need then is, this is our r, our space curve, our vector function. I need the r prime. What's the derivative? What's the tangent vector of this? So, derivative of the first, 2 cos 2t. Derivative of the second, minus sine t. Derivative of the third, that's going to be, I'm thinking of this as ln, it's the ln of t over pi, but I'm thinking of it as using my ln rules, the ln of t minus the ln of pi, so that when I take the derivative of it, the minus the ln of pi derivative is 0. So, long story short, the derivative is just that. So here's my tangent vector. Next, I need the magnitude of that tangent vector. So here's my big square root sign, square root of first component squared plus second component squared plus third component squared. Now, okay, there's the magnitude. So our arc length is going to be equal to the integral from, we're starting at t equals pi and going to t equals 4 pi. This ugly expression, dt. And all we got to do is get a value for this. This is too hard for us to integrate. There's no way there's no simple technique that we know to integrate. We're just going to have to use we'll have to use some numeric value. I'm going to just leave it like this. What is the arc length? It's the solution to this integral. I wonder if we can just ask the machine. Oh yeah, okay. It did Simpson's rule or something and it got 14. So the spiral from t equal pi to t equal 4 pi starting at the point, what point? Well, sine of 2 pi, cos of pi, ln of 1. So that's going to be the point, starting at the point 0 minus 1, 0, and going to the point 0 minus 1 ln of 4. It's 14 long. Let's see what this looks like actually. So it was sine of 2 cos, and okay, that's what this thing looks like. But now let's start at pi and go to 4 pi. So I'm only looking at the part that we're trying to find the length of. So there's our space curve. Okay. That piece of string, let's say if I were to stretch it out, is 14.28, whatever we said. 14.23 long. That's what we're getting the arc length. Notice too that the x component goes through twice as many oscillations because of the 2 as compared to the y component. That's why in the x there's twice as many ups and downs as there is in the y. The z component is just getting bigger with log. Anyway, arc length. What about the arc length formula? And we had to do that numerically. What about the arc length formula for this example? Let's finish this example. Now the idea is going to be the same. This is our space curve, so I need the derivative of that. I need the tangent vector. So it's going to be derivative of the first, derivative of the second. Oh, that's the same. That's just root 2t. And derivative of the third is going to be e to the 2t. E to the 2t. So, oh, that's not the magnitude yet. That's the tangent vector. Next is the magnitude. So if I'm taking the magnitude of that, big square root sign, that makes the integral trouble. First function squared, first element squared plus second element squared. Plus third element squared. And so our length, find the arc length formula. It doesn't give us any t, so I'm just going to have to go integrate from a equal a to b. So integrate from, but just to make it clear, those are times t equal a and t equal b of this expression, dt. Now, maybe we can do this one. Remember I said that they're doable if the thing under the square root sign is a line or a perfect square. I think I can factor that thing under this. It's obviously not a line with that as exponentials, but let me see if I can think about it as a perfect square. Now, how did I think to factor it like this? Well, because that's my only chance, because it's clearly not a line. It does work out to be a perfect square, right? If I do first times first, second times second, plus third, first times first, inner and outer are e to the 2t, so there it is double, last. So then that means that the square root sign and the square cancel each other out. So I can integrate this. That's going to be t plus e to the 2t over 2. And I still have to go sub in the top minus sub in the bottom. So sub in the a minus sub in the b for that value. So this one we could integrate. There's very few examples that are actually integratable. So practicing the ones that they give you in the ones that you see in tests and homework and that means that you probably will have done the exact question or a really close version of it already, because very few of these work out really nicely. Anyway, arc length.